Welcome to the Explainer. So today we're going to break down the actual brilliant mathematics behind how artificial intelligence learns to reason. You hear a ton about AI right now, but have you ever stopped to wonder how a machine actually knows something? And beyond that, how it takes what it knows to draw completely brandy conclusions? Well, let's dive right in and find out. Okay, before we get to the machines, let's look at this Harry Potter puzzle. This is to prove that you are already doing complex logical inferences inside your own brain. Look at the three statements on screen. If it didn't rain, Harry visited Hagrid. Harry visited Hagrid or Dumbledore, but not both. Harry visited Dumbledore. So, did it rain? If you just reason that Harry visiting Dumbledore means he didn't visit Hagrid, and because he didn't visit Hagrid, that first statement means it absolutely must have rained, well, congratulations, you literally just performed logical inference. Now, we're going to build this exact process up, block by block, to see how computers replicate what your brain just did in a split second. Here is our agenda for today. We've got 1. AI and human knowledge, 2. The language of logic, 3. Drawing logical conclusions, 4. How AI checks models, and finally, 5. Teaching AI to play Clue. All right, Section 1, AI and human knowledge, building the foundation. So to build an intelligent, knowledge-based agent, we need a rock-solid foundation of facts. And AI has to understand what it means to actually know something. It doesn't have a human memory, right? Instead, it stores its truths in what we call a knowledge base. Think of it as a set of sentences that the AI agent knows to be absolutely 100% true about the world. It's basically the AI's internal reality. Whenever we want the AI to solve a problem, we've got to feed it a knowledge base first. But here's the catch. How do we get our messy, complicated human facts into a strict mathematical format? I mean, we can't exactly just speak conversational English to it. Moving on to Section 2, the language of logic, the AI alphabet. To encode our world, computers use something called propositional logic. They rely on really simple symbols like P or Q and connect them using specific logical rules. Let's see how this builds, starting with the absolute simplest connective, the not connective. It just inverts our truth values. Simple as that. If our proposition P is false, then not P is true. Like if P is the sentence, it is raining, not P is the sentence, it is not raining. It literally just takes whatever comes right after it and flips it to the exact opposite. Next up is the AND connective, which looks like a little upside-down V. What's super fascinating about AND is just how unbelievably strict it is. It rigidly dictates that both statements must be true for the whole sentence to be true. If P is false, or if Q is false, boom, the whole thing evaluates to false. It only ever gives you a true outcome in that very last scenario you see, when both P and Q are definitively true. Now, on the flip side, the OR connective is a bit more forgiving. The outcome stays true as long as at least one of its arguments evaluates to true. So P or Q is only false in that very first scenario, when both P and Q are totally false. And a quick heads up, in this specific type of logic, OR actually includes the possibility of both being true too. It's what we call an inclusive OR. Finally, we have implication, which means if P, then Q. Now, this one can be kinda tricky. Think of this sentence, if it is raining, I am indoors. Well, if it's not raining, meaning P is false, the implication is actually still considered logically true. Why? Because my original statement made absolutely no claim about what I do when it's sunny. Make sense? And right next to it, we have biconditional. That means the condition goes firmly in both directions, an if and only if scenario. It only evaluates to true when P and Q share the exact same truth value. Section 3, drawing logical conclusions, connecting the dots. Okay, so now that we have our vocabulary of connectives, let's see how an AI uses them to infer completely brand new information. This is where the magic really happens. The absolutely crucial point here is this concept of entailment. If a sentence alpha entails a sentence beta, then in every single possible world where alpha is true, beta must also be true. To put that in everyday terms, if I know one set of facts to be undeniably true, I can definitively guarantee another fact is true based purely on logic. It is exactly how an AI takes old sentences and just magically derives new ones. Moving to Section 4, how AI checks models, the brute force algorithm. But how does a computer actually calculate this entailment? I mean, it can't just think about it intuitively like we do, right? Well, think of this algorithm like a recipe, where the AI enthusiastically tests every possible combination of true and false variables just to see if the knowledge holds up. First, it literally enumerates all possible worlds, which we call models. If you have just 3 variables, that's 2 to the power of 3, or 8 possible worlds. Then, it goes down the list and checks in which of these specific models its existing knowledge base is true. Finally, it verifies if the query it's trying to answer is also true in every single one of those specific models. If it is, boom, the AI has successfully made a logical deduction.
And our final section, Section 5, Teaching AI to Play Clue, Unleashing the Logic.
All right, enough of the abstract math symbols and tables. Let's see this logic engine in actual action. We're going to apply everything we just learned to teach an AI to solve a murder mystery. If you've never played, the classic board game Clue relies entirely on deductive logic. Basically, 3 cards representing a suspect, a room, and a weapon are randomly hidden in a sealed envelope. The players hold a hand of the remaining cards, and they have to figure out exactly what is in that envelope by a process of elimination. So, to teach an AI to play, we have to perform something called knowledge engineering. We turn every single possible person, room, and weapon into a propositional symbol that is either true or false. Is the murderer Colonel Mustard? True or false? Is the room the ballroom? True or false? We're basically mapping the entire game out as simple variables that the computer can easily hold in its memory. Now, look at how we translate the basic rules of the game into a massive logical equation for the computer to digest. We tell the AI, the murderer is Mustard, or Plum, or Scarlet, and the room is the ballroom, or kitchen, or library, and the weapon is the knife, or revolver, or wrench. This gigantic, long, logical sentence, that becomes our starting knowledge base. As the game progresses and cards are revealed to our AI player, we start feeding it negative knowledge. This is where it gets really fun. If the AI sees the mustard card in its own hand, it knows for a fact he absolutely isn't in the envelope. So we add not mustard to the knowledge base. And we systematically do the exact same thing as other players make guesses and reveal their cards. Not kitchen, not revolver, not plum. We are rapidly eliminating variables from all those possible worlds we talked about a minute ago. And this brilliantly illustrates how the AI's model checking algorithm narrows down the absolute truth. The AI looks at that initial rule that it had to be mustard or plum or scarlet. It then sees the new facts we fed it, not mustard and not plum. Using pure, unadulterated propositional logic, it deduces exactly who committed the crime. The only remaining possibility must be true. It was Scarlet in the library with the knife. Which brings us to a fascinating final thought. If this simple propositional logic allows an AI to systematically solve a complex board game with just 9 variables, what happens when this exact foundational reasoning scales up to millions or even billions of parameters? It's just an incredible foundation, leaving us to wonder just how powerful the structured reasoning becomes inside today's massive artificial neural networks. Definitely think about that the next time you ask an AI a question. Thanks so much for joining me on this explainer, and keep questioning the logic behind the machines.